You see my screen?
Yeah.
Nice. Okay, so some quick logistics as usual. Let me copy this. It should already be there in our previous chat. Let me check. From the last session, I probably will copy from there. Yeah, here it is. Okay, I'm going to repaste this here. So if you wanted to contact us in any ways, the first two emails, support@decoding5G.zone, sponsor@decoding5G.zone. Appreciate you reaching out to us. All the tools and everything that we use for the tool for this particular course costs money. So any donation will be welcome. And you can register. Please ensure that you register for the future events. This is the fourth line here is the link for it. You can go and register. And when you register, it will send you the reminders and things like that. So that way it's easy. And the last one is, if you are lazy to go to the Eventbrite and then join the sessions, just copy and paste this in some notepad, or you can create in your own Outlook some meeting invite. By just clicking this, you will be able to join. Right. So those are the key messages that I wanted to give from the logistics point of view. You guys can hear me okay, right? I have a little low voice today, but hopefully you guys can hear me.
It's got it. It's fine.
Okay, perfect. So you all know what is Decoding 5G.zone. The target is, it's a non-profit initiative. It's not a for-profit initiative. It's basically done together by the volunteers, whoever is participating in the session. And only those who are participating in the sessions are the ones that you guys see. But behind the scene, there are around 10 to 15 different volunteers are working on multiple different activities to make this happen as a non-profit initiative. The goal is to really help individuals to skill up and innovation up on 5G technology. That's the thought process. And what we wanted to really do, this is our fifth session. For those who have not attended the previous sessions, what you can do is you can go to YouTube. Let's see if I can quickly. You can just go to the YouTube and you can search Stopper. So this is the nonprofit organization, which is basically organizing this session, right? So you can go to the playlists. There is a Decoding 5G.zone. You can click, and then you will see last 5 sessions. This is the 6 sessions, actually, right? Last 5 section recording. So those who have missed can always go back and listen to that video. Okay. Awesome. So now you have everything that is related to the logistics. Like I mentioned, what we wanted to really achieve, I think it's a 12-session program. This is a 6th session, and we have 6 more sessions. What we wanted to really achieve is 2 things, right? One thing is we wanted to help you guys to build both theoretical as well as on the practical aspects of whatever expertise that you would require to build your 5G knowledge, right? So that's the 5G knowledge / expertise. That's our first goal. And then the second goal is we wanted to see if you are able to, kind of download the practical open source Magma and play around by yourself and able to do end-to-end calls with multiple different, tools that are available out there to get a feel of end-to-end, end-to-end 5G network, right? So that's the second goal, and we call it as an ecosystem. And for this, I had to really thank Wave Labs for providing their labs for people to kind of play around and learn end-to-end ecosystem from their innovation and research labs. So these are the 2 things that we wanted to really achieve together as a team. So every session, what we do is we start with first 20-25 minutes on the theoretical aspect, and then the remaining 20-25 minutes on the practical aspect. So far, what we have done is we have on the theory aspects, we have understood, the evolution of the wireline networks, and we have understood the evolution of the wireless networks. And in the wireless networks, the number of things that we have understood. Today, what we will learn is concept-wise, just a refresher of the core network and radio, followed by transport network and network slicings, right? So those are the 4 key areas that we will slightly touch upon. And the first 2 areas, which is core network and radio network, is something that we have already learned together in our previous session. You can always go and look up the video to do that. And after that, Sashidhar will jump in and he will continue the hands-on practical aspects of it. In our last session, what we did was in the previous sessions, what we did was we were able to help you guys how to download the Magma, how to install the Magma, and how can you use the simulators to make an end-to-end call. And then what we started doing is getting into the depth of the call flow, right? So in our previous session, Yokesh did a wonderful job of explaining the registration call flow and different messages, and he practically executed it, and he showed that in Wireshark, and so on. And today Shashidhar is going to continue on the PDU session aspect of it, so you guys can understand the remaining portion of the 5G end-to-end call flow in a more practical sense. Okay, so let's continue the theoretical aspects and try to talk next 20 minutes before we hand over the session to Shashidhar. I'll pause here for any questions before we move on. Is all good? You guys can hear me well? It's all good?
Yes, sir, we're all good.
Perfect.
Yes.
Let's learn something together today. So on the wireless networks, what we can just refresh a quick one. What we learned was the evolution of 1G to 5G, and we learned 5G is custom built for connected industries. Right? What does it mean by connected industries? Is enabling different industries with whatever that they require, the tech stack, whatever is required to enable different types of communications. Right? Before evolution of the wireless technology, we were doing only person-to-person communication. 4G, we started doing person-to-mission. And now with 5G, we can do not only person-to-person, person-to-mission, and mission-to-mission communication. Because it's ground up built for the connected industries, ability to provide the higher throughput, lower latency, and massive connections of IoT devices that can enable us with a number of different use cases. And we strongly believe that 6G will be the continuation of the 5G and further enhance all the parameters that 5G supports today, from latency to the throughput. Plus, it will take the automation and intelligence of the network to the completely a new level, right? So that's the kind of an understanding that we had. Then we started understanding the end-to-end network, starting from the air interface to the radio, to the transport network and the core network and the management aspect of us, BSS, OSS, and so on. Then we got into the depth of how the different types of networks evolved over the period of time. This number of things has happened, and 5G as such can today, like I mentioned, help us with a lot of use cases for connected industries, from mission to mission to person to mission. And also, not only that, it can also enable and help you with business critical and mission critical applications. In the earlier generation, you were just supporting the use cases that are just business supportive use cases like voice, data, messaging, and so on. But now you can monitor the airport and you can monitor the air control, train control. So business critical, mission critical related use cases also it can support. And we looked at the high level architecture of the 5G network, and then we jumped into the core network architecture, and we learned different network functions within the core network architecture. One of the key message before I move on is to really understand 5G is designed like a Web 2.0, probably will support Web 3.0 related style, right? It's called as a service-based architecture style. No, most of the interfaces are defined through HTTP protocol, and the payload are taken through either JSON or XML, depending upon how you design it, right? So that's going to really help us to enable a very flexible and disaggregated network we can design because of that, right? So that's the key message I want to give you. And we also talked about number of different network functions, and most importantly, I like to kind of bring up this NWDAF. This is the one which is going to at least from the core network point of view, it's going to put the network to a level of connected intelligence, right? Connected intelligence, okay? Because the NWDAF is nothing but it's a data and analytics function, and it allows you to collect different types of data from the core network and see what exactly is happening, and then you can take actions based on what is happening and what's going to happen in the future. These are all the step towards the fully connected intelligent networks and use cases and the future of ours, right? So from the core network point of view, NWDAF is going to play a critical role there. Then we started looking into the radio access network. And what we understood was, because we are focusing on a disaggregated deployment in 5G, even in the radio network, there is a lot of changes compared to the 4G. So they kind of splitted the radio separately, and then the control plane separately, and then the user plane and data plane separately, and they came up with a nice architecture with different new interfaces. And each of these different functions does different things, right? Like we discussed, RU is the radio side, DU is the data side, and CU is the control side. And on top of all these things, what is also more important, like NWDAF in the radio, you have RIC, near real-time RIC and non-real-time RIC. These are the intelligent nodes in the radio side, which will enable you again to build a connected intelligent radio network, right? So these are all the domain. These are called as a domain intelligent nodes. Like NWDAF is for core network, and near real-time RIC and non-real-time RIC is for the radio network. And then you can have one master management entity that can control all these domain entity to build the end-to-end connected intelligence and automated networks. Okay, so when I say connected intelligence and automation network, means you are able to run the network automatically with minimum manual intervention. It opens up the intelligence, it opens up the innovation, and it brings AI to really help to build the automated network. Then the other most important thing that I wanted to share, which connects to next 5 minutes that I'm going to talk about transport network, is the different ways that you can split the radio network, right? The way that I explained last time is the radio network has different stacks, right? The physical layer all the way to the STAP, and then the application RRC and mobility management, session management, and so on top of that. So depending on how you are going to slice and dice these different layers of the stack, you can build different network function, disaggregated network function, right? Like, for example, if you're going to split at this level, you can have RU, right? And even RU, you can split it into two, RU high and RU low, right? Depending upon how you wanted to do it. Then DU can support some physical layer, high level physical layer, and then the MAC layer and RLC. CU can support PDCP and SDAP, right? So this is how the network functions are defined based on which stack level it actually supports, and enables the disaggregation of the RAN network for us to deploy it depending upon various different use cases that demands for you to deploy, right? In some cases, you might wanted to deploy everything together as an aggregated node. In some cases, you wanted to just split RU and keep DU and CU as an aggregated node. In some cases, you wanted to split all the three and do it. And it completely depends on the use case that you're going to do it, right? And the way that you split, the different network functions are defined, and also it's also defined as options, right, in the standards. So if you're going to split CU and DU/RU, it's called option 2, right? And if you're going to split just RU and keep CU and DU, it's going to call as an option 8. So this is a very basic thing that you need to understand, but it's very easy. Just slicing and dicing of the stack in different ways gives you multiple different options, gives you multiple ways of deploying the RAN network in a disaggregated way. That is the most important thing that you need to understand. So why I wanted to kind of stress upon on that is, to jump into this transport. But before jumping into this transport, just to cover this, today, if you actually look at it, the way the radio networks are designed, multiple phones are covered within an area, right? And moving forward, because of a lot of different technologies that are out there at our disposal right now, from MIMO to beamforming to complex technologies, right? We would be able to really do a beam for a particular user and move the beam around wherever he goes to provide a very dedicated, low latency services and so on, right? So these are all the different technologies that allows you to achieve that in the 5G technology, and all that 5G promises for us to achieve for different use cases. Okay, now having said that, I just go back to the RAN stack split and CU/DU. Having said that, what's more important to understand is you have a devices, right? Like phone, then you have a antenna, which is RU, right? And then you can have a RAN that is split into DU and CU, and then you can also further split it. But just for the simplicity, let's say you have a DU and CU. Then you have a core network, and some of the core networks can sit in the edge, like UPF can sit in the edge, but in this diagram, the UPF and SMF, UDM, AUF is actually sitting in the centralized cloud, right? But you can also split these network functions and put it in the different location depending upon your use cases. But the message that I wanted to give you here is that all these different network functions, RU, DU, CU, and all the core network functions, all has to be connected together, right? So what enables that connection is the transport network, right? All the wires and cables, routers, hubs, switches, aggregators, disaggregators, everything that makes up your transport network. And transport network runs not only within the premise, but also runs across cities and even countries under the seas and things like that, as you guys know. Okay. So now when it comes to the transport, that's what the transport network is all about. So when it comes to the transport network, there are few terms that you need to remember: front haul, mid haul, and back haul. Wherever you go, you would probably hearing these words or discussing these words, or these words are discussed in a forum, right? So you need to basically know what does it mean. So you already know what the devices are, you already know what the RAN is, core network is, and different functions are. When it comes to transport, whatever that connects the RU and DU, right? So it's normally from the antenna all the way to the DU, they normally call it as a front haul. Remember these words, right? And then the one that connects DU to CU and all those kind of things at the edge, they are called as the mid haul. And then which connects to the central cloud somewhere in the national or even citywide or whatever, right? Statewide and so on. Those are called as a back haul. So just remember these three things, right? So front haul, mid haul, and back haul. Those are the words that are used for the transport networks that connects the different network function in an end-to-end 5G network. Okay, now it's that these three words, right? Front haul, back haul, and mid haul and back haul. In the olden days, I just kind of put it here: access, aggregation, and core. These words are also used, right? So access can also be repeatedly referred for front haul. Aggregation can be repeatedly referred for mid haul, and core can be repeatedly referred for back haul. So just remember these words, right? So the different lines that connects all the different types of devices, aggregation devices, and all in all these three areas makes up your transport network. Now, transport network has its own technology, right? In the 4G, it was using CPRI, OPSI, right? But in 5G, there are a number of different technologies that are available that can enable you, depending upon the different use cases, different types of speed, right? 100 gig to 400 gig to 500, 400 gig, right? So what you see here are some of the technologies. Mostly nowadays, eCPRI is used on between RU to DU, right? And then between DU to CU, mostly it is F1. And then on the core network, it's mostly the Ethernet 100 gig to 400 gig Ethernet, right? It can also be an optical network, OTN and OTUs and so on. But what is important for you to understand is these are all the different transport networks and technologies that connects all these different radio radio to core network from the point of view of front haul, mid haul to back haul in the transport network. Okay, and the transport network also plays a very, very critical role, right? So 5G promises 10 millisecond latency means it's not just the radio network provides 10 millisecond latency. Okay, it's a combination of radio network, core network, transport network, and even in some cases the management network. If there is a query back and forth together, it has to provide that kind of a low latency, so you can do applications that require for the low latency and so on. It's not only low latency but also for the high throughput and high capacity as well. Okay, so this is the transport network. The bare minimum, you need to understand that. Now it's that you have devices, you have radio, you have core network, you have transport network. In the past, what happens is the whole network used to be a monolithic network. Okay. And now the 5G brings in a concept called a network slicing. And what it can do is it can split the network into multiple slices, right? Like a bread slice, multiple slices. And each of these slices has its own characteristics, meaning you can allocate the radio resources, core network resources, transport resources, and also the infrastructure resources. Because I have, even though we talked about RAN, core, and transport, we kind of forgot the infrastructure, right? The infrastructure, what I mean by that is different servers, because nowadays all these radio core and everything is software only, right? So the software basically sits in the servers, bunch of servers in multiple data centers or in a dedicated devices, right? So you have lots of infrastructure available, and then you have an infrastructure software that manages those infrastructures, like virtual machines and containers managed by different platforms like OpenStack to Kubernetes and so on, right? So that also an infrastructure. So combining your radio, transport, core, and infrastructure, everything together, you can build either a monolithic network or you can slice and dice all these resources to build multiple different network sliced network. Okay, let me put it like that. So each of this network slice can support one particular use case. So if you look at from the 5G point of view, we have three things, right? One is throughput, high throughput, low latency, and massive machine communication. So you can either do the slice as these three slice, or you can even do the slice as different use cases and services that you provide. You can build your own slice for automotive. You can build your own slice for agriculture IoT. You can build another slice for enterprise to support an enterprise private LTE. You can create another slice to do FWA. You can create different types of slice to support different types of use cases, right? So this is the very powerful feature in 5G, where you are able to slice the biggest network into multiple slices, allocate the resources from radio to the transport to the core to the infrastructure that is required to provide the SLA, that meaning service level agreement for that particular use case that you're serving from that particular slice, right? This is a very important concept that you need to understand. And the standards in 5G is defined, which allows you to do this end to end, from RAN to transport to core to infrastructure to the management entities. Okay. And last but not least, what I wanted to talk about is a private network. See, in the olden days, what happened was the barrier to entry was very, very, high. Meaning, if we need to know any of these technologies, 2G, 3G, we got to really work in a big companies to really know that and learn that. Right now, because of the innovation and the open sources that are out there, every one of us can make our hands dirty and learn how to deploy end-to-end network. And a lot of innovative companies have born, and I believe continue to born, to support deploying number of small networks, right? It's no more required to build one monolithic network to serve everyone, but you can build small networks to serve different use cases and different communities and different enterprises. So the way that most of the experts envision is moving forward, you're going to have multiple smaller networks, either independent, dedicated smaller networks, private networks, or network sliced based private networks that will be available. And that all networks has to be managed rather than managing a monolithic network. The problem space is completely shifted, right? From managing from one monolithic network to managing multiple networks, because it will have its own challenges. So that's something that I wanted you guys to really keep that in your mind. Just to sum up, before I give it to Shashi, so monolithic network is public networks, private networks are all small networks that you can deploy with all those beautiful open sources that are available, or closed source that are built by companies, many companies like CELLULAR and many other companies, right? You can build the private networks. So this particular slide is very simple, a slide to sum up whatever that you have learned so far in the wireless network, right? So the left-hand side is the public wireless network and right-hand side is the private wireless network. Mostly public wireless networks are provided by the service providers like telecom service providers, satellite service providers, web service providers, and so on. And private networks, you can actually, provided by the smaller, provided to the smaller enterprises and different verticals like manufacturing verticals and so on. And you can also provide those services to the enterprises through network slicing using the public network. On the private network, smaller network, you can provide that as a dedicated network to them. And mostly the public networks are owned by the providers, and dedicated network can be owned by the enterprises, right? Let's say, for example, Wavelabs can help to deploy the private on-premise dedicated network and help them to maintain it, but the network can be owned by the enterprises, right? And mostly the public networks is used for business-driven communication. Private networks can be used for business critical and mission critical. But if you use the network slicing-based public network, you can still deliver business critical and mission critical applications. It's a trade-off, right? Do you want it to keep everything in-house and build a complete dedicated private network for yourself, or avail the private network provided as a network slicing by the service providers and deploy in your enterprise? It's completely up to you to decide which way to go. There is never one shirt fits all. It's depending upon the different use cases. You choose what is the right network and right technology for you. Okay, so I will pause here, and in our next session, we will start learning about other additional adjacent technologies that makes up the network more intelligent, right? Like cloud, NFV, SDN, and so on. We will start learning from the theory point of view in our next session on adjacent technologies. And then we will start learning about standard and open sources. And last but not least, spectrum, right? So in next 6 sessions to 7 session in the theory slide, this is what you will learn. By end of the session, right, you would probably understand a big picture, theoretically end-to-end picture, and also practically how to really, develop and build and deploy and monitor the, smaller networks, let be a FWA or private networks. Okay, I'll pause here for any questions. Hopefully it was useful, guys. Awesome, perfect. Hey, Suresh.
Yes, Kader, this is
Hopefully my
awesome.
voice was okay. I was a little bit struggling.
Yeah, perfect. You're fit today.
All good, Karan.
All right, perfect, awesome. Okay, I'm going to stop the screen share and hand over it to Shashi there. Shashi, all to you. The second 30 minutes of today's session is hands-on learning through the open source Magma. Go ahead, Shashi.
Let me know if my screen is visible, right?
Yes.
Yes.
Much visible, Shashi. Are you nervous? Are you okay?
No, I am okay. All good.
Awesome. Go ahead. This is the way we get there.
So I'd like to take a minute to just recap on what was covered in the previous practical sessions. So we in the very first session we demonstrated how to install Magma and how to fire it up, and along with it we also connected to the open source simulators, that is the OAI GNB. And the second session, that the follow-up session, also had where we explained in detail the registration call flow. So today we will be going through the PDU session demo. So in this session, we'll be going through what is PDU session and what are the important parameters that are involved with it. We'll touch upon QoS flow. Since QoS flow in itself is a very important topic, we'll be covering it up in depth in the upcoming sessions. Then we'll take a look at the message exchanges and the call flows, followed up by PCAP analysis. And finally, we shall end it with a short demo. Okay, sounds good. Let's go. So till now, we have understood how exactly the UE registers itself, how the core network is able to authenticate that UE, Now, what happens? How exactly the UE communicates to the data network? So once the UE is registered and is connected, the UE requests for a PDU session. So a PDU session is required for the UE to actually talk to the data network or to exchange any traffic or any information to pass from the UE to data network or vice versa. So we can define it as PDU session provides an end-to-end user plane connectivity between the UE and the data network through the UPF. Or terms, we can say that PDU session is a set of connections from UE to GNB, then GNB to UPF, and UPF to data network. Let's now take a look at the PDU session parameters. So the first one is PDU session identifier. What exactly is it? As the name suggests, PDU session ID is an identifier of the PDU session at the UE and as well as the core network. What is SNSSAI? It's basically the slice identifier. It refers to the slice network slice in which the PDU session is created. Then what is DNN? So DNN stands for data network name, and DNN is the name of the data network to which the PDU session provides connectivity. PDU session type. This defines the end user protocol carried by the PDU session. It can be either IPv4, we have IPv6, we have IPv4, v6 as well. Gone? Oh, sorry. Yeah. So in 5G, the quality of service is managed at a QoS flow level. As we understand, there needs to be a PDU session created for the traffic to flow, and within this PDU session, there is a QoS flow. So what exactly now is QoS flow? So QoS flow is the lowest granularity within the 5G system on which a policy or charging can be enforced. What exactly it means is QoS flow carries all the characteristics like latency or data rate or priority. So different QoS flows have different characteristics. QoS flow is identified by QFI. So QFI is nothing but the QoS flow identifier. So when a PDU session is created, always there is one QoS flow that is created along with it, which is called as the default QoS flow. This QoS flow remains until the lifetime of the PDU session. So whenever to sum it up, whenever UE latches onto the network and is registered and authenticated, at least one PDU session is created for it, and then a default QoS flow is added to it. This default QoS flow will remain up to the end of the PDU session. Moving on. Within this PDU session, there can be multiple QoS flows based on the requirements of the service. So for a UE, there can be multiple PDU sessions. Similarly, depending upon the type of traffic, there can be multiple QoS flows within the PDU session. And every quality of service flow will have its own unique characteristics based on, like I said, latency, priority, and data rate. And all these QoF flows are identified by a QFI, that is QoS flow identifier. Now let's take a look at this very important diagram. So there is our UE, or this is our mobile device, or you can call it CPE. And then we have our RAN, that is here GNB. Then we have our UPF, that is nothing but user plane function. And beyond this, we have our data network connected through the N6 interface. So let's now take an example, or the yellow part is your PDU session. When the PDU, every UV will have can have multiple PDU sessions. Each PDU session, there is a single tunnel that is created between the GNB and the UPF. And on the radio side, we have radio resources that are allocated, which are called, which are termed as data radio bearer. So a single PDU can consist of multiple data radio bearers and multiple QoS flows, but a single PDU is mapped to a single tunnel. Whenever, let's take a scenario. Whenever the UV goes active, suppose we have, let's take an example of an OTT platform. What happens first? The UV first is registered and authenticated, and then a default QoS flow is created here. Once the default QoS flow is up, it then requests for an OTT service, suppose Netflix. Then what happens is whatever the service requires, all the resources is passed on to the PCF, that is policy control function, and then a new QoS flow is created with the required characteristics. So the new QoS QoS flow which is created will have all the traffic leading to that OTT platform. And all the PDU session creation, deletion, and modification is taken care of by SMF. On the like I said, so the QoS flow. Suppose the UV requires another service like a WhatsApp video call or something. If the current DRB is not supporting that particular QoS flow, it creates another DRB, and then that QoS flow is taken forward. Now summarizing. So what we did here is we understood how UV talks to GNB and the UPF, how the QoS flows are formed. So a PDU session can have multiple QoS flows. A PDU session can have multiple data radio bearers. A PDU session is mapped to a single tunnel. Data radio bearer is allowed to support can support one or more QoS flows, and so on. So let's take a look at the call flow. So we have our CP or the RAN. Then we have our MME AMF. We have mobility D. We have subscriber DB, which stores all the information of the subscribers. We have session D, which is nothing but the SMF. We have policy DB, which stores all the policy information. We have pipeline D, which is nothing but our UPF. So what happens exactly? The UV sends the PDU session establishment request. It lands on AMF. AMF then forwards this message to session D, that is nothing but SMF. SMF fetches the required policy details from the policy DB and then forwards it to the pipeline D. The pipeline D responds back to the session D, that is the SMF. The session D then responds back to the AMF. And the AMF then sends a PDU session resource setup request to the GNB, and it piggybacks it with PDU session establishment accept message also. So what happens here is the PDU session resource setup request lands on GNB, and if the GNB is able to allocate all the resources which are required for this PDU session, then it accepts it. And the PDU session establishment accept message is sent or is forwarded to UE, and the GNB also sends a PDU session resource setup response back to the AMF. Take a negative scenario when the GNB is not able to allocate all the resources. What it does is it simply drops the PDU session establishment packet, and then it sends a reject message back to AMF. So just to summarize again, what happens? UE sends establishment request. It is forwarded to the SMF. SMF fetches all the policies, and then it is forwarded to pipeline D. Pipeline D responds back. SMF responds back to AMF. Here, AMF sends a PDU session resource setup request saying GNB, these are my resources which are required for this PDU session. Are you able to allocate it? So along with that, it also sends an establishment accept message. So once the GNB is able to allocate the resources, it basically forwards this establishment accept to the UE and sends a response back to the AMF. Let's now take a look at the PCAPs. So till now, up to this session, we have seen how we have seen all the messages like the initial UE message and the initial contact setup response. All the registration and the authentication flow is covered. So let us take a look what happens after the registration complete. Like I said, the UE will send the AMF a PDU session establishment request. So then what happens is AMF sends to the GNB a PDU session resource setup request. So this is the same request which is happening here. Basically, it tells Gnode B that whatever resources are allocated, are you able to allocate it? Like yeah. So after that, what happens is it is piggybacked with PDU session establishment accept message. So PDU session establishment accept, if everything goes well, what the GNB does is basically whatever message we piggybacked, it takes it and it forwards it to UE. And it also sends a PDU session resource setup response back to AMF. So now let us take a look at each request in detail. Let us see some of the identifiers, what information is passed. Okay. So starting with PDU session establishment request, this message, like you can see, it is sent from UE to AMF. This is the very first message. This message is basically for the PDU session creation. Okay? And what happens is you can see the message type is PDU session type, and we also get PDU session establishment request. Sorry. And we have the PDU session type, which denotes whether it is IPv4, IPv6, or IPv4v6. Then we have the request type, whether it is an initial request. Then we have the SNSSAI IE, that is basically saying which slice the PDU session will be, and the DNN. Here the DNN is given as internet. Then what happens is the AMF sends a PDU session resource setup request to the GNB. So what this request has, what this message has. So it contains elements like PDU session aggregate maximum bitrate, basically PDU session AMBR. It has both for the DL, UL, and then we can see some tunnel information. The IP address of the core is sent here, and then again the PDU session type, whether it is IPv4, IPv6, or v4v6, and then it also is given some of the it also contains some of the QoS flow parameters, which we'll cover in the QoS flow session. So followed by this, what GNB does is it tries to allocate all the resources. If it is successful, this is the success message which it sends to the AMF. So it contains the PDU session ID. It contains the some of the tunnel information, like the IP address of the UE. The IP address of the GNB, and it also contains the QFI, that is QoS flow identifier of that particular QoS. Then moving on, final message which happens is the PDU session establishment accept. So what this message contains is all the QoS roles. Again, it contains the PDU session type like IPv4, V6. It contains the QoS rules. It contains information about the session AMBR, how much for the downlink. That in this example, it is 2 kbps. For how much for the uplink, it is 1 kbps. It has PDU address. This PDU address is nothing but the tunnel IP address. Which after the PDU session, whatever the tunnel is created, so that tunnel interface IP address we will get it here, and then it has NSSAI, which is basically the slice identifier. So which slice the PDU session is established, and then we have the DNN, which is internet here. So summarizing again, in Magma we have this what we do is we piggyback it. So what we do first, UE sends the PDU session establishment request to EMF. EMF sends EMF sends it to SMF. SMF takes policies. Then this SMF forwards it. I mean the session D forwards it to pipeline D, which is UPF. Then pipeline D responds back to SMF. SMF responds to MME, and then what happens here is the PDU session resource setup request is piggybacked with PDU session establishment accept. And once the GNB is able to allocate all the resources, this PDU session establishment accept is forwarded to UE, and PDU session resource setup response is sent back to the AMF. So now let's move on to the demo. So in our demo setup, it is the same setup that we had in the previous session. We have the orchestrator where we are able to add all the subscriber information. We have the AGW, which is our Magma. We have the GNB UE simulator, which we are using is OAI GNB simulator, and the data network, that is the internet. So let me take you through the demo just a second. So in this, up to now, what we have done is we have installed our Magma, which is distro Magma. You can see we have our OAI GNB UE simulator, and we have fired both of them up. Now both are running. So we will start with the point where we just take a status of, check the status of the MME. So we are So we'll check whether all the services are up. Magma D, pipeline D, all the as you can see, all the services are up, and then we verify again by checking the process ID of MME, and then we are going to basically do a packet capture. So so we turn on packet capture, and then we tail our syslog. Then we also tail our MME log. Then followed up by we'll fire up the OAI GNB. Yes, OAI GNB is up. We fire up the OAI UE. So now we'll take a look at the MME log. A note that the MME log has the debug. The log level is debug. So you need to manually set it to debug in order to have all the extra logs which you get from debug. So we will start from registration complete, as this was the message we left in the last session. So after the registration complete, the UE is completely registered. It is authenticated by the network. Now what happens is we can see that PDU session establishment request has landed on AMF. So we can see that here. Then once the AMF creates the tunnel, creates all the resources required, and then it will send a PDU session establishment accept message. Okay, so once now we have our tunnel up, let's check the interface which it has created. So OAI tunnel UE1 is the interface, and it has an IP address ending with 13. So let's now try to flow some traffic by pinging 8.8.8 through the tunnel which we created. So as we can see, the traffic is flowing, and we are getting the ping is continuing. So I'll just fast forward it to, and just, yeah. So after that, what we did, we killed the ping, we killed both the UV as well as the GNB. I'll just fast forward. Yep. And then, yeah. So here are some tables which we can see, the OVS tables. So table 0 represents the incoming table. We can see the N packets here, which it displays. And then we have the OVS table 13, which is for the QoS flow. We can see it here as well. And then the outgoing table, which is the table 20. So we can verify that all the traffic was actually flowing through the tunnel. And as an additional command, we have this this command to check from which IP block is the IP assigned to the tunnel. Then we also have this command which shows exactly what IP is assigned to the tunnel. So, yep, that's about it for the demo. Some coming back to the PPT. So just summarizing what all we went through. What is PDU session? It basically provides an end-to-end user plane connectivity between UE and the data network through the UPF. Then we saw the basic, what are the basic parameters, the PDU session identifier, the NSSAI, DNN, PDU. And then we followed up by touching upon QoS flow. What is QoS flow? It is the lowest granularity on which the policies and the charging are enforced. Each QoS flow will have an identifier. Then we also saw that there can be multiple QoS flows based on the requirement. And also they are differentiated based on their characteristics like priority, latency, data rate. And we also saw that every PDU session will have at least one QoS flow, which is the default QoS flow having the lifetime of the PDU session. And then we also saw how exactly the flow happens from UE GNB to the UPF. On the radio side, we have the DRB, which is nothing but the radio resources which are allocated. On the GNB, in between the GNB and UPF, we have the tunnel, and the data network is connected through the N6 interface. We saw how this exact flow happens. So PDU session establishment request is sent, and then the pipeline descends back response, and then finally AMF sends a resource setup request saying to GNB, and then also it is piggybacked with establishment accept. Then we get a response back from the GNB, and this establishment accept message is forwarded to the UE. And we saw a couple of PCAPs as well. Yep.
Wonderful, Shashi. Excellent session. I really enjoyed it. Any questions from anyone to Shashi? No? All right. So I have just put my LinkedIn in the chat. Those who are not connected with me, please feel free to connect with me. Yeah, go ahead, Fatima.
Yeah, Kader, in the interest of the group, I have a couple of questions for Shashi. Shashi, can you talk about what is this OVS table? Because you are talking about OVS table. Maybe somebody new to the 5G may not be able to understand. Can you say a short content about what is this OVS table all about?
During whenever the tunnel is created, we have couple of, this OVS table, we record all the, the incoming packet data and the whatever QoS flow data is there. So in table 13, we have the QoS flow data, and that which is the outgoing, we have the table 20, which have the outgoing packet data.
Yeah, maybe I can add a little bit.
Yes,
so
Yogesh.
OVS is so OVS is an open vSwitch. It's an open source project which provides the fast path processing of the packet. let's say our Linux kernel can still process the packet without it, but then it will behave like a general purpose OS. With OVS, what happens is we provide a pipelined architecture which helps packet to navigate fastly within the Linux. So it's like a software-based fast path, an equivalent of a router which is there at our home. So it provides a faster packet processing in the kernel.
Thank you, Yogesh.
And
Yeah.
then, yeah, it does with various tables, whatever Shashi was mentioning. It configures the table so that that pipe is created.
Exactly. Yeah. Yeah. Thank you, Yogesh. Yeah, the last line makes sense for everybody. It acts as an router where the incoming packets and outgoing packets are mapped, and it makes it into fast path. That's the important point. All of us has to take away message for all of us is to, instead of a normal Linux kernel, this OVS adds to the fast path and it does the routing of packets from incoming to the outcoming in a faster way. Yeah. Thank you, Yogesh. Over to you, Kadar.
Thank you, Parthiban. Yeah, so like I mentioned, I put my LinkedIn in the chat. Those who are not connected, please feel free to connect with me. And also don't forget to, copy the links that I sent in the chat. If you don't want to register in Eventbrite, you can click that Cutly link to join in our next session, which is going to happen in 2 weeks. But I sincerely recommend you go to the Eventbrite and register yourself so the reminder comes and you remember, because even for me sometimes, because it's bi-weekly, I tend to forget last minute, oh no, we have a session, and then we got to prepare. So I just recommend you guys to register in the Eventbrite. So yeah, what else? Thanks for joining. Wonderful session. I really appreciate Sashi for your crystal clear, very, very precise explanation. Really enjoyed your session, and I trust everyone else also enjoyed your session. So with that, let's close for today. You all have a wonderful day, and talk to you guys soon. Bye-bye.
Yeah.
Thank you, Kadar. Thank you, everyone.
Bye.
Thanks.
Thank you.
You all.
Thank you, everyone.
Thank you.
Thank you.
Thank
Thank
you all.
you, Indra.